Yeah. Yeah, that works.
Can I erase it now?
Yeah, but again it will start to autofocus.
So I'll leave it there. All right, welcome back. A couple of administrative announcements. I can now confirm that we have at least 2 TAs. Ankit Agarwal is sitting up in front. Ankit, wave your hand so we can all see you. And Chitradeep Patara is sitting way in back. Chitradeep, wave your hand. Okay. We will have probably one more before next week. We're working on some details around that. I have also posted office hours for myself. I will also post office hours for the other, TA yet to be unnamed with the first draft pick. So the other team will also have office hours, and then it'll hopefully, give you all time to meet with us as well as use the discussion forum, which I see some people already use, which is good. I have put up a link to Tuesday's lecture. Because of the way the live streaming works, the lectures are pretty much ready as soon as they're done. Is that correct, Ankit?
Yeah.
The lectures pretty much, are they archived as soon as they're done?
Yeah.
Okay. So we will make sure to put the links up as soon as the lecture is over. I've also linked the lecture notes for the lectures material that covers Tuesday as well as today. I have also put up reading material, as some of you had asked, for background on recurrences, divide and conquer, greedy algorithms, and such as so on and so forth. This is again basically a collection of Jeff Erickson's notes, but I linked to the specific chapters, so you can take a look at them. This will be useful because there will be a first homework that I will put out tomorrow, and we'll have a short window for you to work on. Mainly because you can use this as a diagnostic to figure out, should you be in this class or not, right? And I'm sure that won't be a problem, but just in case. So this should give you a sense of things you should be at least somewhat familiar with and be fairly comfortable with. And if you're not, you should come and talk to me, or and we can discuss what it doesn't mean that you can't take the class if you're not comfortable. But there might be other ways we can deal with the situation. As far as the class mechanics go, that's pretty much all I have to say for now. Next week I'll have more information about dates for constructing your project groups and coming up with your initial ideas and how you might go about it. Okay, and one of the questions of the forum was basically, do we need at most 2 or 2? And it is, the person correctly pointed out that at most 2 could mean 1. And yes, that is right. However, I would not advise it. That what I expect you to do in the project is A, a fair amount of work, and B, will involve dealing with material that's relatively complicated. And it's nice to have a sounding board to interact with. So if you can, try to start talking to your friends and try to form a project group soon. Probably within a couple of weeks, the first task will be due in terms of what you have to do for the project. It won't be much, but you will have to do something. Any questions on last time's lecture on the various components of hashing we were talking about? Yes, Daniel, right?
Daniel.
Yeah.
When we talked about choosing a random hash function, so the adversary could see, we're assuming he could see the possible hash functions that you could choose, right? He doesn't know which one you could choose. Right. So since the adversary could still get lucky that in the sense that you choose a hash function that he was hoping you would choose, then would you still have to detect a collision and choose a different hash function if you're getting bad performance?
No, the adversary is a sort of a conceptual device, right? It's a device to analyze the algorithm. The adversary doesn't actually exist. So in other words, when the algorithm is not saying, okay, hey adversary, what are you doing? And I'll do something different. The algorithm is going to choose whatever it is. The adversary is used as part of the analysis. So we can say, what is the probability of having a problem? So I'm not saying there won't be a problem. What we're going to say is that in expectation, on average, there won't be a problem. So these are the kinds of guarantees you give to randomize algorithms. And I'll talk more about that today. We'll talk more about that. Any other questions? Okay, so let's continue. So if you recall, last time we had talked about different ways we might solve the dictionary problem, namely, if you're wondering, this big AF is in the middle because the camera is not smart and needs something to focus on a big white screen. It'll get erased as we get closer. Right? This is the question that we wanted to solve with biometers. And we looked at many different ways of solving this problem. We talked about deterministic solutions. We talked about why, because of the pigeonhole principle, you can guarantee that you will never get a satisfactory answer that runs in constant time. We talked about solutions that work in log n time, which are fairly easy, assuming an ordering of the universe. We even said, this issue is not so serious. You can construct an ordering of the universe as long. We talked about a solution that does give you constant time query access. What was that solution?
The big table solution.
Jared?
Michael,
see, he moved.
Is that there?
So, go ahead.
It was the big table solution where you had a table as large as you, and you just It was like a bit table,
Yeah.
ones and zeros.
And I'm pretty sure many of you have implemented some kind of big factor lookup for some problem. And so this is not a bad solution, right? This is a perfectly reasonable solution. But what could be bad about it?
It takes a lot of space,
How much space?
on the order of U.
And U is bad. And one way to think about this is that imagine U as, my favorite example is, U is a set of all IPv6 addresses. So you're talking 2 to the 64, right? And your router is storing some small number of them. So then U is 2 to the 64, you don't want a 2 to the 64 size table. That would take a while. I know we're in big data, but we're not in that big data. So we're still looking for, and so we talked about the fact that since any deterministic solution is not going to work for us, right, we want some kind of randomized solution. Then we talked about building some kind of magic hash function that has some property. Does anyone remember what that property was that I wanted for that hash function? Anyone from that side? Anyone? Yeah.
Was it that the
Remind me of your
distribution?
name again?
Chris,
Chris.
the distribution of the, as the set of the elements of S go into the hash function, they're distributed uniformly.
Can you be more precise?
So we had a table of n elements, and as the elements that we want to store go in, they're distributed uniformly.
That's not exactly what we wanted. We wanted that as the goal. That was not the condition though. Do you remember the condition? I mean, that was the desirable outcome of the condition, but that was not the condition itself. Anyone in the middle section want to take a crack at this? Yeah.
We should be able to.
Srinivas.
Yeah. We should be able to uniquely identify every element. We should be able to uniquely identify every element in U with the map. I mean,
That's the desirable goal. That's what you want. But again, that's not the condition of the hash function. So the condition of the hash function was something like this, that for all pairs x and y that belong to U, the probability over a hash function chosen at random, this is the notation I'll use for this thing. So some set of hash functions and I'm choosing one randomly. The probability that h of x is equal to h of y, given that x is not equal to y. That doesn't make sense. Is equal to n, where h is a function from U to the set. This was the condition we wanted, right? What we wanted is that the probability that two elements go to the same location is 1 over m. Why 1 over m? Well, because there are m slots. So what we're saying is that if you put an element somewhere, the probability that any other element ends up in the same spot as that is uniformly distributed over the table. That's where the uniform distribution part comes from. Yes?
Could we also just say that for given the size of the hash table, we expect an equal amount to be set in each, plus or minus 1 if you have like a non-off?
You could say that, but that would be a lot harder to enforce. This does that in expectation, right? So what we said next was that if you have this condition, I made this claim, I didn't actually show you, that if you look at the load on a particular bucket, so you look at a bucket I, and you say what is the load at I, the number of elements at I, then okay, then what we said was that the expected value of L of I for any I is equal to n over n, which is a sort of a probabilistic expression of what Danny just said. That we want it to be roughly even. And we're saying, in fact, an expectation it will be even. Even, of course, because you have n buckets and n things. I didn't prove this, by the way, so it might be instructive to sort of see how you go about it. Is that all? You remember this from last time? Okay, good. So now how do we prove this statement? How do we show that the expected value is indeed n over n? So one way to think about this is that you define an indicator variable. So we'll say that C x comma y, okay, let's see, is equal to 1 if okay. So this is what is called an indicator variable. It's a signal of the thing we're trying to estimate. And again, now let's assume that x is not equal to 4. So clearly this variable will shout 1 if something bad happens, right? This is an event that something bad has happened. So this is the way we construct your question.
He was wondering if C meant anything specific.
Actually it does, it means collision. But no, it's just an arbitrary choice. I just happen to choose C being collision. But no, otherwise, yeah. But that's why it's just a mnemonic, so I can remember. So this is what we do in randomized algorithms. We say there are events that we, either want to make sure they're small or make sure they're big, and we want to count up the number of these events. In our case, the things we're counting are the load on a cell. So a bad event is when two things collide, and so we're trying to measure that by doing this. So for any given location, we fix an x that goes in there, and we can now say something. And again, this is given in more detail in the notes. So we can say what is, the number of items. So let's say that h of x is equal to j. So it's some number j. So let's look at the load Lj. Well, the load Lj, and this is the key, is going to be the sum of all Cxy for y belonging to S. Right?
Question real quick. In your definition of C of x and y, do you need that condition that x is not equal to y for the value 1?
I just realized about 5 seconds ago that I don't. Well, yeah, it doesn't really matter. I can leave it in there. I can remove the condition, it'll all work out just fine. Yeah. So the trick here now is that I've expressed the function I want to analyze, this load function, in terms of a simple combination of these variables, which I hope to be able to analyze using my procedure. Okay, and it's as simple as that it's a sum. And we'll see in a second why it being a sum is such a good thing. Okay. Because now if I wanted to do what is the expected value of L of j, that's equal to the expected value of the sum of all these things, right? Yeah. Okay, but here's the thing that you must tattoo on the insides of your skull, if you haven't already, which you may have. Expectation is a linear function, which means that, and this is the key, this can be rewritten by swapping the summation and the expectation. In other words, this is a very innocuous step. It's a very important step. It only works because expectation is linear. For example, if you're using variance here, this won't work. Variance is not linear. But by linearity of expectation, you can swap the sum and the expectation. Which means now instead of having the expectation of a sum of things, you have a sum of an expectation of things, and the things are very simple things. These are just 0, 1 random variables. Okay? And now what we know is that we can now say what is the probability that any of these CXYs are going to be 1? Well, we just said that. It's supposed to be 1 over n. Because that's a property we want of our hash function. So the probability of two things colliding if they're not equal is 1 over m. So this number, CXY, has an expected value of 1 over m. So this just becomes and I have now proven that the expected value of the load is n over m. Done. Okay, and we'll call this number alpha as a load factor. I'm going to use this load. Okay? Any questions about this? Yes, your name?
Ian,
Ian.
how do we know that expectation is linear? Is that just a general property of an expectation function?
It is a general property of the expectation function, and you can prove it.
Okay.
The expectation of a random variable is this, it's a discrete random variable, is the sum of the probability of the random variable taking a value times that value. So in other words, right? So you can now say, okay, what is the expected value of x1 plus x2? It's equal to the, let me see, so this is equal to probability that okay, I'm not going to do this here. I will put up a note on this. There's a proof of this. Basically, you basically show that the expectation of x1 plus x2 is equal to expectation of x1 plus expectation of x2. You can show the expectation of 5 times x is 5 times the expected value of x, which actually you can see from here. Once you have those two properties, you know it's linear, and you're done. So sorry, it's like running a demo on the fly. You never do it. So I'm not going to do proofs on the fly, so, unless I prepare it. But I'll put up a note. Okay, so that's all well and good. And my hashing problem is now solved finally. Or is it? Yes?
Do you need the C to be independent?
Do I need the C to be independent? I will ask you another question first. What's your name? Sorry? Winin. Okay, thank you. Do I need them to be independent? No. And that's the beauty of linearity of expectation. It does not require independence. It's true regardless. And intuitively this is because it's a linear function. The expectation is a linear function. The variance, which is not a linear function, requires you to understand correlations between things, and then you need independence to make things work out nicely. But for expectation, you don't. Okay? So no, they don't have to be independent. That makes our life a lot simpler in doing this. So why are we not done? Yes?
Do we need to formally define how we generate our random hash function?
We do. We have not yet specified where this magic pony hash function is coming from. How do I generate a hash function that has this desirable property? So remember, I did this in a very weird way. I said, give me a function that satisfies a property, and I will give you the world, and I'll give you a hash function. I'll give you a hashing structure. But I haven't told you how to make that function. This is no good if there is no function that satisfies that property. So can someone come up with an idea for a hash function that would satisfy that property? The property of this the universality property that this. Anyone? Michael.
Take each 8 bytes times by 31 plus it by another, the next byte, and just keep doing that over and over again for every byte.
Take each byte, multiply by what?
And then add a C to it or something.
You know that it's going to work.
Well, this is what Java uses for their default hash.
It's what Java uses, therefore it must be correct.
It's not a very good hash function, but
It probably isn't, yeah. There has been some notoriously bad hash functions that have been used in early incarnations of various programming languages. There was one that like the default thing that used to be used for C, called random, was sort of well known to be terrible. Yeah. So one of the things I like to say in algorithms class is, it's very healthy to be dumb. It's very healthy not to be clever, let me put it that way. So the reason I say this is because you don't want to put filters on where you say, okay, I need to come up with a nice smart answer because he's asked this question. That's not the way we actually discover new things now. We start by asking very, very simple questions and coming up with very dumb solutions, and then realizing where they don't work and trying to refine them to get something more interesting. And that process is as important, as I said last time, as the process of getting the answer. So what is the simplest possible answer you could give? I want someone who hasn't actually put their hand up yet. Preferably someone whose name I do not know, so you can help me learn. And you need enough positive examples to learn people's names. Yes, your name?
Craig.
Craig.
Just like modding it with power
explain?
Just taking like, if we want to put it in like.
So what about 10 buckets? Yeah.
Just do mod n.
Mod 10. Okay, so good. So Craig's hash function is that's it?
Yep.
Okay, so suppose, okay, here's my input.
It's not a very good hash.
That's right, and you're perfectly correct. But the thing that you've missed is that this is still deterministic. And remember that I just implemented the adversary to use the pigeonhole principle to kill your hash function. Because I found the two roommates, or the many roommates here. Can you come up with a random hash function? That's really, really simple. Yes, your name?
Boya, you just add a random number to x every time before you mod it.
Okay, so that's what you're saying? Where R is chosen uniformly at random from where? From, let's say, from U. Let's assume that U has the plus operation on it, so I can do this kind of. Okay, is this a good hash function? Yes.
It can go beyond the
Your name?
group.
Guru. Yeah, okay.
It can go beyond the place, so we'll have to mod it again or something.
But it's already put a mod in.
No, I mean the hash, the site R into model. It's
Oh, sorry.
No,
Sorry.
so.
There has to be a modem, yeah.
Okay.
Chris. Ian. Ian. Should have known this. I told this 5 minutes ago.
Well, doesn't that not guarantee that if you put in two of the same object from the universe that you'll get the same answer out since you're picking a random variable?
So an interesting objection. So here's an objection to your function. Normally I'd walk you guys in the room and have you fight it out, but okay, we do it. So his objection to your function is that if I put in x twice, it'll go into different locations. So I won't know anymore when I ask is x in the set, if it's there or not.
You could have a table that stores the,
Pardon me?
you could have something that stores,
R?
yeah, R and then U.
Okay.
So it's sort of like a,
So she comes back with store R, and now I'll know the next time I get X, I just have the R for that. Counter?
Then how do you know which R matches up? Now you need a hash set for the R's.
Oh, he brings the recursion counter move. Okay, so his counter argument is that if you did that, now you need another hash table to store which R for which X.
you could just use an array.
Just use an array.
Linear lookup time.
Linear lookup time. You could just talk to each other, but you know. No, this is good. This is. By the way, this is exactly how we do algorithms. Usually it's in our head, so it just sounds strange because I'm just talking to myself and people didn't create. But normally that's how it's happened as the adversary back and forth. So linear lookup time. If you use a simple array.
So like by linear lookup time.
Well, okay, so let me rephrase. I think what his objection is, and correct me if I'm wrong, is that if you store the R's for each X in an array, and you now have to figure out for a new X, okay, what was the R I used to put it in, you have to now look it up in that array. So that if you don't do another hash table, then it's going to take a while to look it up.
I was actually just thinking that you know that, like, say X is at 0, then you know that R would be at 0, then there's no lookup involved.
But suppose X is 573.
So you use the same index to look up R.
So it's the same R for all of them?
No, I mean like for, so say like you were going through the X's and you want to know, like, say you're going through 21 in your list, and then you know that 21 is at index 2.
But how do I know that? I need to know the R, right? Because I took the number 21, I added R to it, and the answer was 2. So there was some R value that gave me that answer 2. The next time someone says, hey, I gave you 21, you still have it. You know, you need to know what that value is. So the problem is this. And this is a very good point that the two of you brought up. Fine. This is good. We'll have to get together to act together. This drama again next time. So this is great. So the problem with a random hash function, and it's not hard to come up with, this is a very good random hash function, the one you suggested, it works great, is that if you really choose a random hash function, its complexity is very big. You actually have to store all these values. In particular, another kind of hash function you could pick was, which is very similar to what, in fact, the general version of what you said is basically h of x is a random element of n, which is exactly what you said because you're just adding an r to make it random, and that's what we'll do. And the problem with these things is that they seem to require lots of bits. And so now you're thinking, well, maybe I'm just not clever enough. I need to think harder about the right way to encode this hash function so I can do it without all bits. And I'm here to tell you that's not going to work. I don't care what cool method you come up with. It is not going to work. Do you believe that I can even make such a statement? That I can completely destroy your hopes and dreams without even knowing what they are? Do you think that's credible, first of all? Yes, you had a question?
The third method you said h of x is a random element of m.
Yeah.
So how do you actually pick a random element of m? So
How do you pick a random element from M? How do you pick a random element from a set?
do you need
Not good at
something-
volume 2, 2.3.1. That's a standard way to do it. So you think of it this way. It's an M cells, you have log n bits, choose each bit at random, 0, 1, you get an, there are many ways you can do it. So do you think what I'm saying is even possible? That I can sort of just dismiss all your methods without so much as a why or leave? So this is the awesome power of Mr. Shannon, Claude Shannon, father of information theory. Here's the thing. How many hash functions are there that you can imagine in this universe? Remember, a hash function has to go from u to m. How many such hash functions are there?
Infinite.
Infinite? No. Can't be infinite. I hope not anyway. Last time I checked. Yes?
So however many bits you need to store to represent all m things, so it's 2 to the power of whatever.
Are you answering the question of how many hash functions there are?
Yeah,
Okay, so go on. So 2 to the power of...
of m, or whatever is needed to store m.
Well, let's think of it this way. To write down a hash function, what do I need to know? I need to know, okay, for the first element of u, where does it go? Second element of u, where does it go? To say where does it go, how many bits do I need?
Is it factorial to you?
Maybe, but can you tell me why?
Because if you have 3 elements and then 3 elements here, so you have 9 maps. So
No, but let's think about this, right? So I have a mapping, any mapping from u to m, for each element of u. So let's think of, I have all the elements of u. For each of them, I have to tell me, I need the hash function to tell me where they're going to go. So I need log n bits for this first one, telling me where it's going to go. I need log n bits for the second one, right? So how many bits do I need?
U log n.
Another way of saying this is that the number of hash functions, forget hash functions, the number of functions from u to m, so this cardinality of h, is equal to, and so if you take logs, the number of bits you need is u log n. Yes?
Isn't this only characterizing deterministic hash functions?
I'm looking at all hash functions.
Well, to say that it always maps x to a particular bucket would mean that it's deterministic, right? So you could have a non-deterministic bucket that maps x to a different bucket each time.
It could, and that's when you get into problem because now you have no idea and you can't find something. Right. But remember, the hash function itself is deterministic, but it's randomly chosen. Right? It's like I have a bunch of balls on the table of different colors. I pick one of them at random, but the ball doesn't change its color as I look at it. Okay? So that's the setting we're in. Yes?
Could we make that work by just saying that you're correct with some probability by having a sort of random hash function, and then we just run it a lot of times, and eventually you're likely to have whether or not it's in the set?
You could. and that would change the game. Remember the game we're playing here. The game we're playing is a dictionary game where I really want to know for sure if X is in the set. If I'm allowed to change that game, what I get is a Bloom filter. A Bloom filter, you might say something is in the set when it's not. It has a certain false positive ratio. And you do it basically along the lines of what you guys are talking about. It's a different kind of hash function. So you're perfectly it's perfectly okay to play that game, but the game has now changed. Right? So let's understand the game we're playing right now, and then we can talk about that. So, okay. So what I'm saying is the following. There are n to the u possible hash functions. I am required to produce one such hash function. I don't care whether it's being produced randomly, deterministic, what have you. I have to have one. To write down one element of a set of size n to the u requires a log of that many bits. Right? That's just basic entropy. And so I have u log n. So if I had to write down a fully random hash function, I need u log n bits. That's a lot of bits. I just ruled out a solution which used u bits. I said you can't use that, it's too big. It's 2 to the 64. So this wonderful hash function that I wanted to produce, which has all these nice properties which I haven't proved, but is easy to see from the definition function, is too big. And that's the problem that you guys are facing, that you could not come up with a representation that was small. No matter how hard you try, you won't be able to because of that. And that's what I mean. I can rule out an entire class of solutions just based on information theoretic arguments. Okay? Any questions about this? So now what do you do? We're in deep doo-doo here. I gave you this nice property, said, oh, life is great, expectation, blah, 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 load balancing, woohoo, and now I don't have a function for you. And this is where we come to this idea of pseudorandomness. Okay. So, too big. Pseudo. I'm going to write it down. We've always talked about time and space as resources. That we want to minimize time, we may want to minimize space. But if you ever worked with random numbers, you realize that randomness itself is a kind of resource. It's something that's hard to generate a lot of. To get truly random bits is tricky, no matter what kind of good generator you might have. And so you try to use as little of it as you can get away with for your particular problem. And the study of how much randomness you really need gets us to the topic of pseudorandomness, where in some sense you take a small number of true random bits and put them through some amplifier that gets you lots of pseudorandomness. And the reason you do this is because if you have to use 10 random bits, that's 10 bits of space you need. If you can use those 10 bits to generate 1,000,000 pseudorandom bits, then you don't actually have to write down 1,000,000 random bits. You can use the 10 bits, do something on them to make 1,000,000 pseudorandom bits. Now this is not happening for free, there's no free lunch here. We're not producing randomness out of thin air. These bits are inferior bits. You have the little bits of rust on them and stuff, and they just don't look so good, But they suffice for the problem at hand. And that's the key, to understand what you really need for the problem at hand. And it turns out that for the problem we're looking at, the problem of building a hash function that has universality, so that two things collide, roughly uniform problem, we do not need the full power of a random function over all the space of all hash functions. All we need is something a lot simpler, called pairwise randomness, pairwise independence. And that suffices. And because we don't need a lot of randomness, you can actually make that into an algorithm that uses very few random bits, and therefore is actually small in space. So effectively what I'm saying is that instead of going from the space of H, which is equal to all hash functions from U to N. This is too big. We don't want to use that one. We're going to use another hash family, which is much, much smaller. And now we're going to choose randomly That's the plan. Okay? The plan makes sense? Okay. So how do we do this? So the idea is this, we're going to do some number theory.
Professor, can you go back to the previous slide?
Yeah. Actually, I'll keep it on while I'm checking this.
Professor?
There's a question.
Should we choose randomly from each, right? So,
From H prime. Yeah. So the number of bits we need now is going to be log of the size of H prime, not log of the size of H. So that's going to be the way. Okay. All right. So let's look at one particular example of what we could do. So what we're going to do is, we're going to choose pick a prime number that's more than u. There's a well-known fact in number theory called Bertrand's postulate. Remember the postulate? We covered it in the end of your class? Okay. So Bertrand's postulate says that if you take any number and double it, somewhere in the middle is a prime number. Which is very nice because if you have to go hunting for prime numbers, it's nice to know that you don't have to look very far. Take any number and you can try to solve this for small prime numbers. You'll see. 20, it's very easy. So we can choose a prime number p that's more than u, but in particular it won't be much more than u. It'll be less than twice u, which is going to be important. Okay. And then what we're going to do is, we're going to define the following function. We're going to define a hash function. So also fix some a that belongs to 1 to 2 to p minus 1. Okay. Then define h sub a of x equal to a times x mod p mod n. Okay. This is a hash function parameterized by the number a. So a couple of things to note in this hash function. Let's deconstruct it a little bit. This, of course, is the easy part. Why do we need this? Because we're putting it into a table of size n, right? So we need some index. So that's the easy part. The interesting part is this. If you've done any number theory or any kind of group theory, one way to think about what's happening here is that by taking an a and multiplying every element, multiplying x by a, and then doing it mod p, you're essentially rotating it in the circular group that's the prime field. Okay? This is the way to think about it. So you have this prime field, which is sort of 0, 1, p minus 1 going round and round, and taking a just turn around, and then take mod n. Okay? And then my class is a set of all hash functions for A belonging to. We'll call this class just. I'll put a plus there to show that you're not counting the 0 element. Okay, so this is a class of hash functions. All right. Okay. How big is this family? How many elements are there in this? Your name? Ian. There are p minus 1 elements in this class, right? Okay. Yes, the 2 Ians. So there are p minus 1 elements in this class. So h prime is size p minus 1. So how many bits do you need to write down an element of h prime? Log p. I said p is between u and 2u. So we can say that the log of the size of h prime is basically log u, which is good, not u, log u. Right? And since log u is the number of bits you need to write down an element of x anyway, it's actually quite nice. So that part is good. The other part that's more interesting is that, does it satisfy the property that we want? Is it in fact true that if you take two elements, the probability, any two fixed elements, the probability of their collision, when you choose randomly from the set h prime, is going to be 1 over m. And before we get into the proof of that, and the proof is not hard, think about why this, sort of morally speaking, should be true. You look quizzically at me.
Morally.
It's a term I use often, and in my community, no one would blink at it. What I'm trying to say is that it has the feel of rightness about it. When we prove things, right, we don't actually sit down and say, oh, I have a random statement, I'm going to prove if it's true or false. You kind of, this has this kind of, the feel of rightness, and then you go try it. You don't prove it till then. So you poke it in many different ways, you attack it with counterexamples, and it sort of resists all your attempts to break it. This is okay, it glows with the aura of mathematical authority, and now you can actually prove. That's what I meant by it feels right. So why should this have that aura of correctness around it, right? Forget about the proof. The proof is the thing we do to convince ourselves that it works. But why should it be true? That's more important. So what's your gut feeling on this, right?
Because you're making each other relatively primes, there's no way like x and y won't map to the same place because they don't share a common multiple.
Right, so your name?
Sam.
Sam. So what you're saying is that because you're choosing a prime field, things don't accidentally collide, right? If you're doing mod 6, this will not happen, or if you're doing mod 10. Since you're doing mod a prime field, mod a prime number, you expect that things will kind of get separated out. So if you pick things at random, that there's no good reason for them to collide. And if they do collide, it has to happen just by chance. And that's what we're trying to capture. Okay, good. So this is kind of this vague intuition. So you start with this, okay, there's something to do with the prime field, it has to be somehow related to that. Now you can start saying, okay, let me try to prove this. Right? So what is the thing you want to prove? You want to prove that, so first of all, this is the fact we need. And I'm going to state this fact, the proof is in the notes. Right? Basically, that division is unique. In particular, just to make it clear. This is the key fact we're using. That if you have a prime field and you look at a number that's not 0, it has a unique inverse. Right? This is why it's a field. Right? And this is somehow going to be what's going to be important. Right? This fact, and again you can see the proof is not hard. So what's going to happen now? What we're going to say is that we have these two elements now, x and y. We picked a random a. So we did a HA of x and HA of y. Actually, you know what? Let's take a break. Think about this. How are we going to go through this now? Think about this fact. Take a 2-minute break.
Yeah.
What's your name?
For how long?
Okay.
So that's, oh for God's sake.
T for turn.
One more reason to know.
What's the other TA?
It's available in the campus, Chitradi. I mean, the name, the office, everything is available.
Alright, you don't know it.
Chitradi. Chitradi. It's a long name. That's why it's
And you guys have your hours up already?
not yet. We are still deciding because there is one more review has to be finalized. So we are waiting for what time because we don't want the art to overlap and we want to discuss what time.
How many hours do you guys get?
I'm doing this, so I'll be taking less. It depends on the responsibilities.
This basically means that
You know what masters are PhDs?
it's even better, it's much tighter. You could have maybe 3 size. This would still be true. We can, you have a lot of flexibility. You think?
Hello. लेक्चर के बीच में मैं वो लेक्चर को टीवी में मैं एक आधे 1 घंटे में घर पहुँच जाऊँगा, तब बात करने के लिए कॉल कर सकता हूँ जाने का। मैं वही बोल रहा हूँ कि भी कर लो तेरा काम खत्म, मैं भी घर में चला जाता सब काम करने फिर आराम से।
But the thing is that H was huge. It had the size of U log n. H prime is much smaller. Its size is U. No, I constructed it. I constructed it. Much less than what? Much less than, I want, remember, the goal was that I wanted H prime to be much less than the size of H. The size of H was, m to the U. And this size is equal to so
but it will always be the same. If A becomes A dash,
No, they're just saying that you're using a switch track.
I have one that we also have one.
Yeah, so it's mobile. I know. Yes, okay, this is how I think about it. It's not ready for the but it's the right but we all have our good. This is we don't have a we have okay. So this is a good point I want to bring up. This question came up. When I said that multiplying by A is a rotation, what I'm using is basically a mental model in my head that is convenient for me when I think about these concepts. It's kind of what people in the field call a good lie. You know, it's not true, but it's truthy enough. Sorry, Colbert. So it's truthy enough that it kind of works, and it works to put these concepts together. As you get into more involved concepts in algorithms and in mathematics in general, you'll find that there are lots of mental shorthands that you have to use to think about what they look like, and often you'll have 3 or 4 different ways to think about the same thing. And so that's why I call it a rotation. It's more of a permutation than a rotation, but in a certain sense, okay, I'll be quiet. But anyway, that's just to keep in mind. If you're caught up on why is it a rotation, it's not exactly that, it's a permutation. Okay, so we were going to use this lemma, the unique division lemma, and I'll just call it that. I'm not going to refer to it directly. Unique division lemma, to show that our hash function is going to be well behaved. So let's take a particular hash function. So let's fix an A. And if you're thinking of actual hash functions that you use think of A like a seed. Right? That's a seed to generate your hash function. So no, we don't fix A, sorry. So choose A at random, uniformly at random, from E plus, okay? Fix X and Y, okay, that are not equal. We want to figure out the probability that they will be put in the same hash bucket, right? So let's look at HA of X minus HA of Y, right, which is equal to AX mod P mod M minus AY mod P mod M. A number of simplifications later, this will become A times X minus Y mod P mod M. Right? What is the bad event we are worried about? Just look at the left-hand side, not the right-hand side. Based purely on the left-hand side of this equation, what is the bad event we're worried about? The left-hand side is 0, right? We're worried the left-hand side is 0 because we know that X is not equal to Y, and we're worried that they're going to collide, right? So, all right. So the left-hand side will be 0 if the right-hand side is 0. Since X is not equal to Y, somehow we're worried that this whole expression, when will it become 0? Yes.
It's if the result of A of X minus Y mod P is equal to M.
If the result of Ax minus Y mod P is equal to M. Correct. Right. So since X and Y are arbitrary, they could be anything. Let's just call X minus Y Z because that also could be arbitrary or anything. Right. So we're asking basically when will AZ mod P, where Z is not 0, mod M be equal to 0. Okay? Alright. So now, let's think about this for a second. Again, let me make sure I get this right. So I don't make a silly mistake there. So, of course, AZ mod P mod M is equal to HA of Z, right? That's the definition of the hash function. So what we're saying is that given an arbitrary Z, so fix some Z, what is the probability that the hash function sends it to 0? Right? Okay. So the key idea is this. So let me see. I know you're all scribbling very rapidly, so let me give you a second to catch up. But again, all of this is in notes, so you don't have to write it down. So if you like writing it down because it helps you, that's fine. Okay. So remember the question is now, I have this function AZ mod P mod N that we want to check if it's 0 for a randomly chosen game. We also know that for let me see this. What am I trying to say here? Sorry, one second. Yeah. The previous lemma about unique division basically gives us the following fact, that there exists, so let me say this properly. Yeah, so for any x in P, okay, oh, sorry. Okay, there exists a unique A such that okay, so what I'm saying is that the previous lemma said that we had unique division. You can generalize that to say that if I give you a target value x, and I want to say what I multiply z by to get to x, there's a unique thing that gets you there. And again, this is the property of the prime field. There's only one way to get to any particular element of it. So you're starting with z, you want to get to x. This is where the rotation non-metaphor comes in. There's one way to get there. Okay, there's one shift that gets you there. So there's unique A for this, right? So if you think of any particular value of m, so you think of now, again, we're worried about when you're going to be 0, right? So we're looking at the 0 bucket, right, of m. So we have m, we have all the elements of m, and we're looking at the 0 bucket here. And we're saying, okay, what is the probability based on A that you're going to get there? Well, for any z, right, there's a unique A that gets you to a particular value of x. So for any z, there's a unique value of A that gets you to 0. Okay? Because there's a unique one, they essentially, and this is the magic of the prime field, they go uniformly into M because of this uniqueness property. Okay? So there are exactly, basically, there are exactly P minus 1 over M values of A such that AZ mod P mod M will be equal to 0 because of this uniqueness property. Okay. And since there are exactly P minus 1 over M values of A, that will get you here. The probability of choosing one of them is that divided by, so the probability that HA of Z is equal to 0 is equal to P minus 1 over M divided by P minus 1, which is equal to 1. There's just not that many of them, and they're uniform. And so the basic idea of what's going on here is that because you have essentially randomly scrambled your input by multiplying by the seed A, randomly chosen, the probability that you end up at any particular bucket gets smoothed out. So instead of explicitly constructing something that smooths you out, you're doing it randomly. And it turns out all you need is that one rotation. That's enough. that for this particular hash function, to get this particular property, you don't need to choose uniformly over all possible hash functions. You just need one seed value. And that one seed value is how long? You just need one value of A, which is of size log P, which is it's a value P. Its number of bits you need is log P, which is log U. So you just need one extra number essentially to store your hash. And you're done. So yeah, your algorithm is basically choose A randomly from H prime, and then your hash function is H. And there are ways of making this sort of computationally convenient so that you only do things mod 2 to the W, so you can do basically bit shifts. Again, these are the notes. Yes?
Would you then continue using that same hash function for the duration of that hash table?
Yes. So you would choose that hash function at one time in the beginning. And then you start throwing it in.
So as soon as you choose that random A, then there is a worst case, but you don't know that worst case prior to choosing that A.
Right, so so you incorporate the choice of A into the algorithm. So the adversary doesn't get to see what you choose. The adversary doesn't get to see your private random bits, essentially. Yeah, that's why you can talk about the expected value of these things. So when you take the averaging, it's over all universes, where the different universes where you picked A, where you picked 1, you picked 2, you picked 3 with the beard, and that kind of thing. Okay. So over the multiple universes, you do the averaging, and that's what you get. So any one particular one will have its own weird profile of behavior, right? But on average, you'll be okay. That's your hash. It has expected constant level. Any questions? Yes.
Yes. I couldn't understand how you arrived at p minus 1 by m values of A.
Okay. So let me see if there's a clearer way to say it than what I just did. So what I want to say is that so let me draw a picture. So let's again look at AZ mod P, and put a little box here, mod M. What do I really care about? I care about two things having the same value mod M. I care about this being 0 mod M in particular. I'm trying to see what happens when this is 0. So I'm looking at the 0 bucket of the table, of the hash table, saying, okay, what's happening in here? Right? So I'm trying to say, okay, how often is something going to go into the 0 bucket? Okay. Well, something is going to go in the 0 bucket if it's 0. So I need to look at what this value is, which is x. Okay. So what I'm saying is, no matter what value of x you pick any value of x you want, right, in the range of 1 to p minus 1. There is a unique value of a that will, when multiplied by the fixed z, will get you that x. Okay. So think of it this way. So let's write down all the x's. So imagine all the x's, and there are p minus 1 of them. So we have all the x's. And now they're all mod, we're doing the mod m. So this one is going to be 0, this one's going to be 0, this one's going to be 0, this one's going to be 0. And it's going to be 0. So, right? These are the values of x that are 0 mod m. Okay. I'm saying for each of them, right, there is one value of a, not 2 or 3 or 4, one value of a that will get you that when multiplied by z. So there's some, there's some a1 here, there's some a2 here, there's some a3 here, and so on. Okay. Right? Okay, but how many values of x are going to be 0 mod n? That's much easier. There are p minus 1 over m. Because it's going a cycle, right? You have 0, 1 mod m, 1 mod m, 2 mod m, up to m minus 1 mod m, and go round and round and round and round. That's the cycle. So there are only p minus 1 over m of these values, and because each of them has a unique a that gets you to them, there are only that many a's. So this is what's called in combinatorics a bijection argument. You want to count the number of a's I'm going to count the number of x's and then set up a bijection of the number of a's. That's why the uniqueness is very important. Suppose, for example, there were a whole bunch of a's, A3, A7, A10, a whole bunch of them. Then my analysis would break now, because now the probability of getting that would start going up. So this uniqueness is very important. That's why I need a prime field.
Follow up to that, the uniqueness, is it an assumption? Or?
No, it's not. It's a property of the prime field.
Okay.
That's a lemma that I didn't prove, but it's in the notes.
Yeah.
That's why I chose a prime number. Yes.
Well, I was just gonna ask why, but I can choose the notes, I guess.
The why what?
Why it's unique?
Because you have a unique divisor, essentially.
Yeah.
Yeah. That's why. Any other questions? Yeah.
So we're putting x into this equation as though u were the natural numbers between 1 and the size of u, right? So I guess you could do the same thing if you had some sort of number for the set, where you could map it to that range and then put it in the hash function, right?
Yes. So you assume some kind of numeric encoding. So this is what's called an arithmetization trick, right? You take your problem, you make it number theoretic, and then use algebra, you basically use number theory and field arithmetic on it. This is a standard trick we do now for a long time. We take something and make numbers out of it, or we take things and make geometry out of them, and then we apply all the magic of geometry or this case number theory. So look at the dance of things going on here, right? Basically the magic is in the prime field, but all these things have to coordinate and do this delicate dance so this all works out. If you change them, they won't work. You have to pick A at random, you have to have P be sufficiently large, but you don't want to make it too large. Right? You have to make sure you have a prime field. All these things have to work. Okay? Alright. Yes?
Would you, in implementing this hash function, would you have any problem with the number of bits you need for a big lump because B has to be at least as big as U?
How many bits do you need? I need log of B. So in my 2 to the 64 example, I need 64 bits. That's not so bad. There are ways to fix that problem. If you don't like the fact that it's so big, you can actually take your universe and sort of chunk. So what you can do is, so I have a universe that's very big, as you said, right? And my universe can be, think of this as the bit string describing an element of my universe. And I need a prime number that's equally long. I can actually chunk it. I can break it up into 3 bits. Thing here, choose one prime number here, one prime number here, one prime number here, and then write down a linear expression of these things. So you can actually label them. And again, in the notes, just get all. So there are ways to reduce that. One thing I want you to think about now, or I want us to think about now, is the following. I have said that in expectation, you have constant, if you have the hash function with this nice, so we have this whole chain of arguments, right? If H is universal, or more precisely, if the hash family H is universal, this implies O of one axis, right? O of one axis in expectation, on average. If m is equal to theta n, right? Because then n over m becomes constant. But what is the worst case that could happen, even with this? I said on average, things will work out. But if you think of actually putting the things into this table, right? When you actually put it in for any given hash function, it won't be even. It'll be slightly off. In fact, it could be very off. So consider the following question, which is essentially what's going on. All of hashing boils down to taking balls and throwing them into buckets. Okay? Because you can think of the hashing problem as taking your ball, your object, and throwing it into a bucket. So in this case, if I have the hash table size roughly the size of the set I want to hash, you can say that m is equal to n. I have the following question. I have n balls and n buckets. So on. And now you can ask, what is the worst case? Or what is the expected worst case load? In other words, what's the expected value of the max load? Not the expected value of the load, expected value of the max load. That could be a lot worse. And here's an interesting fact, that if you throw n balls into n bins with very high probability, so with very high probability, max Li is equal to seems bizarre now. Ignore the log n for a second, but the basic intuition, this intuition you should keep in your head a lot, is that even in expectation when things are expected to be flat, uniformly distributed, in this case you should expect 1, right? If you have n balls and bins, you expect 1, and in expectation you'll get 1. But if you look at the fluctuations across the bins, and you can write a small simulation to do this, very easy. You will have some bin that gets very heavily loaded. It's actually very easy to prove this. You don't prove it directly, you ask a slightly different question. The question you ask is, what is the probability? So let me write this here. What is the probability that, let's see, that the load on any bin, for any particular bin, is more than some number of k. So that xj equal to the load on a bin j. So you can ask this problem. So what do you think? What's the probability that a particular bin gets more than k things in it with a random, with a hash function? Sure, everything done randomly. So if it's going to be more than, at least more than k, you have to have k things that go in there, right? So you have to choose k things first, right? And so that's so they have to make sure those k things go in there. So the n choose k way of choosing those. And what is the number of all ways of putting things in bins? Well, that's n to the k. Right? So basically, this becomes something like this, which is roughly by what is called Stirling's approximation. I think it's n to the k, yeah. 1 over k factorial. You can expand the binomial expansion and work this out. There's a simple approximation that allows you to do that. So the probability that any particular bin has more than at least k things in it is 1 over k factorial. Okay. And it's helpful to know that if you set k to be something like 2c log n over log n, then k factorial is greater than n to the c. Again, this is just algebra. Put it all in and you can figure this out. Or you should be able to. So what? The point is this. I have said that the probability that some bin, a particular bin has more than k elements, right, is something like 1 over k factorial. Okay? For the max to be more than k, at least one bin has to have this. Right? Yes? So, the probability that some bin has more than k is what is called a union bound. So you say, okay, well, this could have, or this could have, or this could have. So you add up all those probabilities. So the probability that the max is more than k is equal to k over k factorial. Is there k bins? Oh, sorry, not k. N. Yeah, it's n, sorry. N bins. I just said k factorial is n to the c. So you can actually upper bound this number by something like 1 over n to the c minus 1. So the probability that the max is more than k is going to be a very small number, 1 over n to the c minus 1. You can think of that 1 over n squared or 1 over n cubed or 1 over 100, n to the 100, whatever you feel like. It doesn't matter because the c is a constant in k. So it's O of log n over log n. You can also show that with a high probability it'll actually be this value. With a very high probability doesn't get to be more than log n. With a very high probability it actually is around that log n. Okay. This is a simple example of what we call a tail bond. Rather than looking at the average value of a distribution, we're looking at what happens at the tails. And we'll see more of this in subsequent lectures. Because to analyze a randomized algorithm, it's not enough to just look at what happens in the middle. We need to look at what happens with high probability. Or what will not happen with high probability. So that bad things don't happen. So even though we've given a hash function now that has good expected case behavior, we know that it has not so pleasant tail behavior. There are some bins that you could have high load. And we want to discuss what to do about how to fix that problem. And we'll talk about that next time. But in the meantime, I want you to go with one thought. I said that if you throw n balls into n bins, some bin can get very heavily loaded, up to log n over log n. If I throw n balls into a gazillion bins, then presumably things will be much better. How many bins do I need before, with a really good probability, every one is by itself? There are 0 collisions. Obviously you can make it really big, but how small can you make it? N doesn't seem to work, because with n bins I have log n collisions. You might think, oh, I'll just use n log n bins. That won't work either. How many bins do you need before it works out fine? And if you figure out the answer and come back and tell me next time, I will sing happy birthday to you. And that's a clue actually. All right, see you all next week.
Birthday.